As you may already know, our oceans are home to a wide range of structures, from oil platforms and wind turbines to bridge piers and breakwaters. Many of these structures rely on vertical cylindrical piles driven deep into the seabed for stability. These piles are constantly exposed to the powerful forces of ocean waves. Understanding how waves interact with such structures is not just a matter of academic interest, it's essential for safe and economical design. Underestimating wave forces can lead to structural failure, while overestimating them leads to unnecessary costs. That's why engineers must accurately predict these forces using well-established principles of fluid mechanics and wave theory. In this lecture, we'll focus on one of the most widely used methods for estimating wave forces on slender members like piles, Morison's equation. This equation allows us to compute both the inertial and drag forces generated by waves as they move past a pile. We'll begin by understanding the nature of wave forces, then introduce the concept of wave kinematics using Airy wave theory, and finally apply Morison's equation step by step to compute the total force acting on a pile. By the end of this session, you'll have a solid foundation in the principles behind wave loading on offshore structures. Knowledge that is vital for anyone pursuing a career in marine or offshore engineering. Now that we've introduced the topic, let's take a moment to outline what you'll be able to achieve by the end of this lecture. First and foremost, you'll gain a solid understanding of the different types of wave forces that act on offshore structures, particularly on vertical cylindrical piles. These include inertia forces, which arise due to the acceleration of water particles around the pile, and drag forces, which are caused by the resistance of water moving past the pile's surface. Next, we'll explore the most commonly used wave theories, especially Airy wave theory, which provides a mathematical model for predicting wave behavior and particle kinematics, that is, the velocity and acceleration of water particles at different depths and times during a wave cycle. Airy wave theory provides a foundational framework for understanding wave behavior and particle kinematics in shallow and intermediate water depths. Its key results include the sinusoidal form of the free surface elevation, exponentially decaying particle orbits with depth, linear relationships between wave parameters like frequency, wave number, and water depth. This theory is widely used in coastal engineering, oceanography, and fluid mechanics for analyzing wave-induced forces on structures and predicting wave behavior in natural settings. Airy wave profile or the sea surface has a shape of sinusoidal wave. This profile is directly calculated using the equation for surface elevation in Airy theory shown here, where h is the wave height, k is the wave number, omega is the angular frequency, t is the wave period, x is the horizontal, and t is the time. Now that we've covered the types of wave forces and introduced the idea of wave kinematics, let's focus on the key equation used to calculate these forces using Morison's equation as shown here. Developed in 1950 by Morison and his colleagues, this equation is widely used in offshore engineering to estimate the total force per unit length acting on a slender structural member, such as a vertical cylindrical pile, due to wave action. The first term represents the inertial force, which arises due to the acceleration of water particles around the pile. It depends on the mass of displaced water, which includes fluid density ρ, cross-sectional area, and acceleration multiplied by the inertia coefficient Cm. The second term accounts for the drag force, which results from the resistance of the pile to the movement of water past its surface. This depends on the flow velocity squared, the fluid density, the diameter of the pile, and the drag coefficient Cd. Together, these two components allow us to compute the total wave-induced force at any point along the pile. This equation assumes that the pile is slender and does not significantly disturb the wave field, an important assumption when applying Morison's equation. Let's take a closer look at the force coefficients involved, the inertia coefficient Cm and the drag coefficient Cd. These coefficients are empirical, meaning they are determined through experimental studies rather than purely theoretical derivation. They account for the complex interactions between the wave and the structure, including effects like flow separation, turbulence, and added mass. The inertia coefficient, Cm, reflects how much water moves with the structure, essentially the added mass effect. A value of 1.0 means no added mass, while higher values indicate more mass being moved with the pile. The drag coefficient, Cd, depends heavily on the Reynolds number, which relates to the flow regime, whether it's laminar or turbulent, and the surface roughness of the pile. In practice, engineers often refer to standardized tables or charts, such as those found in API RP2A or ISO 19902, which provide recommended values for Cm and Cd based on real-world conditions and laboratory testing. Let's look at a typical problem related to calculation of wave force per unit length. The pile of diameter 1 meter, installed in water depth of 10 meters with wave height of 3m, wave period of 8 seconds, and Cm equal 1.5 and Cd equal 0.8. Our goal is to calculate the maximum wave force per unit length acting on the pile at the still water level, which is typically where wave forces are most intense. We'll follow the same 6-step process. Step 1. Use given values. We already have all the basic parameters defined. Step 2. Solve for wave number k, using the dispersion relation, OBB equals 0.785 rad a second. Solving this equation numerically gives us the value of k, which we'll use in the next steps. Step 3. Compute maximum velocity and acceleration. At the still water level, z equals 0, we compute the maximum values of horizontal velocity u and acceleration a using the Airy wave formulas. Assume after solving, max u 1 equals 0.94 ms per su. Step 4. Plug into Morison's equation. Now plug all known values into the equation to get the total force per unit length.